I'm Carol Chen.
And hey, I'm Cedric Clyburn. Thanks for being here with us. The keynote was amazing, right? That was very cool seeing it felt like magic to be able to go from container file to build a system to then use all the same CI/CD. And hopefully, raise your hand, you were here for the keynote yesterday as well. Sweet. Okay, cool. So if you saw that, you also saw the potential of open source AI. And so what we want to do in this session is practically go from the same technology of bootable containers and going from our container file through those cloud-native processes and getting to that system image, but actually introduce AI to the component in order to build out a code generation application. So this is a very practical use case for organizations that maybe want to use a GitHub Copilot for their developers, an IDE or something like that, but don't want to send their data and their code base to some type of third party. So quick introduction, I'm Cedric. I'm an open source engineer and developer advocate at Red Hat. I make workshops and tutorials and YouTube videos on how to use AI and some of the technicalities behind it. And I'm joined by the wonderful Carol.
Hi, I'm Carol Chen, and actually we have an intro slide, but
oh, we do, yeah.
Yeah, no worries. I'll just quickly intro myself here. I'm a AI community architect in the open source program office at Red Hat. I support various upstream projects, open source projects, obviously, and I work with wonderful communities such as these. And DevConf is one of my favorite events, so I'm really happy to be here, especially with Cedric, to be able to share this with you.
Yeah, absolutely. We're going to catch you up a little bit on what's been happening in the community and the ecosystem for bootable containers. Last year at KubeCon, Red Hat donated a collection of tools, Podman, as well as bootable containers to the CNCF. Bootable containers, as you might have learned this morning, or as you're about to learn right now as we recap you really quickly before the demo, are essentially taking that same type of file structure to build a container file, but actually adding in the kernel when we're building that container image so that we could take that and build and deploy for some type of disk image, maybe for Cal Q2 or Amazon or wherever we want to deploy our actual system unit. And we're going to show you how to do this completely using Podman and Podman Desktop. So you could use the CLI for Podman, but I always do like a who likes Emacs and Vim and who likes a VS Code analogy. For me, I'm on the side where it's like I'd rather use a visual interface so I don't have to remember all of the arguments. So we're going to do that today with Podman Desktop. And if you'd like to see the slides that we're going to be using today, we've got the link for you here, or you could go to Pretalks, right? Yeah, Pretalks, and also get that here. But we're going to recap you really quickly, show you the potential for these AI workloads. So we're going to take an inference server. We're also going to take an open source model, and then that front end of a Python application, and combine that all together to deploy that on our local system, or maybe share it with others. So again, a quick plug for, or sorry, not again, but a quick plug for Red Hat Dan on Tech. So this is a show that I produce with Dan Walsh on a lot of different technologies such as Podman and bootable containers, but also just you can find it on YouTube. And if you're interested, we interview people who are working on these projects, and we get that in-depth demo and analysis of what you should know and what you can do with these technologies. Okay, sweet.
Oh, you moved the slide.
I guess.
Okay.
I guess so.
Nice.
Well, Carol.
All right. So now imagine deploying your entire operating system with the same ease and consistency as your containerized applications. So bootable container make this possible. Unifying system deployment and application management into a unified way of deployment. Sorry. Do we have the clicker?
Oh yeah, I can get you the clicker.
So some of the complexities about infrastructure and organizational stuff. So for the most part, operating system seems like a solved problem, but actually looking closer, we realize there are a lot of challenges when people and organizations intersect with technology. So depending on your industry or background, some of these listed here may or may be more relevant than others. So I think I'm still on this slide. Yes, oftentimes different platforms tend to require specific tooling. For example, teams with specific platform expertise. While that in itself isn't necessarily a problem, there's inherent overhead and complexity that requires more coordination, and that impacts velocity. Another common challenge is the time required for testing and validation. In practice, particularly regarding OS updates. In practice, budgeting rarely accounts for maintenance and upgrades of the OS and the applications running on top. And let's not forget security, one important thing. So these are just some of the things that become hurdles when we get into the operating system space and how everything's connected. On the application side of things, containers solve similar problems in terms of packaging and delivery. The adoption of containers was much faster than the previous virtualization and cloud computing waves. This really had a profound impact on the way people share applications. The key lesson here is that containerization technologies and workflows provide just enough standardization, structure, and ease of use. Containers are becoming ubiquitous. If you can build them anywhere, we do it in production, in our scaling them using pipelines, or even independently on our laptops. So this one building block, the container, has spurred quite a whole ecosystem. I think bootable containers are a natural evolution of container technologies. For over a decade, containers have evolved into an industry standard of bundling, shipping, and deploying applications. Bootable containers build on top of these existing technologies and extend containers to include the entire operating system, along with the Linux kernel, as shown here, to allow for a comprehensive container-native workflow and user experience. Actually, Cedric already touched a bit about this in the beginning, but that is just a simplified illustration. A bootable container image ships the entire OS, the kernel, bootloader, and drivers. The ultimate goal is to install the content of this bootable container image on a host. Updates to the hosts are also applied via bootable container images. So this means that we pull from a standard container registry, just as we did for application containers for over a decade. So Cedric, tell us more about bootable containers and what the process looks like.
Sure thing. Yeah, so as you've seen maybe in the keynote or you're about to see here in the demo, essentially we're bundling a lot of tools that already existed, so OS build, RPM OS tree, to essentially create a file system and then package that together. And so what we're actually able to do is package this as a container, right? So I push this to my registry, others can pull. But the thing is, once maybe I've taken this and built this into an image, right, which is the entire OS with the kernel, we're able to essentially just do a pull from that registry to update the system. So this allows us to use that existing CI/CD, and we'll actually show it here in a second how the diagram looks. But the heart of it is this tool called Bootc, which we're going to use the CLI today to actually be able to manage and maintain this system. So let's say that, hey, I pushed a new update to this application. I can essentially just go to the registry and pull that down instead of having to do an entire new OS upgrade or anything like that, and make small edits perhaps with like DNF or something on the system that need to be replicated to all the systems, right? So it's integrated very well with systemd. So we're actually going to be running our containerized application as a system unit with Quadlet. And then there's updates that you can do or rollbacks. So let's say you push that update, it doesn't work, we just roll back to that system. Essentially, when we do this, we start from that container file, right? Instead of using, say, for example, CentOS Stream, we're going to be using CentOS Stream, which is built for bootable containers, which includes that kernel. We're going to show you the container file that we use to do that. We build that image, right, and we push that to a registry. And the first thing we do is convert it to a disk image to deploy it in a variety of different formats. But then once it's out there, we just go ahead and do an update with Bootc upgrade on the actual system itself. Or we could set a cron job so it's just done automatically or event-based. So so you start with that container image, and then you can update systems just pulling down that new image. So it's pretty awesome to keep all of our existing workflows, but now be able to deploy on system host. So again, I talked about that bootc command line. So these are the main commands that you got to know is, hey, bootc upgrade, can I check for a new version or a new tag that's been released? Or should I roll back to the previous state? Maybe it's a completely new image, right? Maybe we're trying to deploy a different workload. We would switch to that reference image. And there's more commands here that we'll check out in the GitHub. That's where the documentation is for bootc. Now, you're probably wondering, how do you build a container? It's the same way that you've been building containers, but now instead you're actually using this specific bootc image. And you can make your own bootc images as well. So there's maintained and supported ones for Fedora, CentOS, RHEL. I think Alma Linux is also supporting it now. So a lot of different distributions. But essentially, you're just using that base image, installing what you need, copying in those configuration files, and running configuration scripts such as, hey, podman run this specific image. Or say, for example, I'm pointing to a quadlet or a .cube file. So you can customize it. And let's actually check out some of these images as well. So as I mentioned, Fedora, CentOS, and RHEL actually have these supported distributions, but there's others. And I've seen people in the community create their own, which is pretty cool. But if we go over here, and again, this is in the slides, or if you go to pre-talks, you can view this. You can see that, hey, you've got these base images that you can begin using today for your systems. And also, there's an idea of, hey, how much do you need? Like, do you want the full image or the base image? So if you've worked with RHEL as a universal base image, you know that there's specific ones for, say, Python, or minimal ones so that I only deploy, the least amount of, kind of units possible. Or sorry, not units, but, packages. So full and minimal, but again, you can make your own. And if we actually go to CentOS Stream 9, which is what we're going to be using today in the demo, we can see that on GitLab, you can actually see the entire repository that's used to build that image that you can pull. So it's using Conflux to actually build that. But let's go over to the container file, and you can see essentially how this is done, like the sauce behind, behind the magic, right? So if you maybe wanted to do this yourself, you could, or you could use this as a best practice. As you can see, you're starting off with the actual container base image, but then essentially building that file system out, installing things like SE Linux and RPM OS tree, tagging it, making sure that, hey, it's known to be a container, but it's a bootable container. And then to finish it off, we're signaling, hey, it's a container down here as well. So if you want to learn how to do that, check out the repository. But we'll come back here to the slides and keep going, because this is great to know that, hey, there's these base images we can use, but there's an extension that will allow you to essentially build these images to not only, with Podman Desktop, build your application image, but the bootc image as well. So we're going to be taking a look at this extension in Podman Desktop that allows you to build for your specific architecture. If you're deploying, say, for example, to Amazon, you could upload your EC2 key. You can add in other parameters during this build time, and it's going to essentially just kick off a podman command that's going to bring in the image builder container. It's also going to bring in your bootable C container and build that for your specific architecture. So highly recommend checking out. This is what we're going to see. And if you'd like to, if you'd like to deploy for RHEL, for example, you get these additional benefits certifications. And I highly recommend you check out this free hands-on lab. So it's like a Katacoda type of scenario where you can get started and try out the utility for yourself. But now that you know about bootc, how it works, how you can use it, how does this relate to AI workloads?
Yeah, good question. So first of all, here are some common use cases for bootable containers. A lot of these are pretty standard and expected. For example, the one-to-one with app and host, as many organizations continue to use VMs as the primary isolation. And this results in running one primary application on each VM. Many of these deployments will benefit from being managed as a unit and can become more appliance-like with image mode. I wanted to mention about edge appliances as well. Edge deployments often face a number of environmental challenges, not always connected. and constraints. So the value of having image-based updates, where a system goes from known good to known good images, is desired from a stability standpoint. We also gain resiliency, and this being able to kind of roll back to this type of capabilities is a big step forward. But I think for us here, we are most interested in the AI ML stack. So this is a relatively new concept, as we have to think about, well, we're all kind of running AI workloads essentially on Linux. So to be able to perfectly version the app dependencies, the kernel dependencies, the GPU accelerator drivers, and everything else into one stack is really important. As often, these are tightly coupled or purpose-built to work with runtime frameworks. So with that, much of the world already leverages containers for AI workloads. You can think of NVIDIA Inference Model, or NIM, which encapsulates AI inference models within containers. Having these in a bootable container can allow us to deploy and run AI stacks quickly and efficiently, and as close to the hardware as possible, so there are benefits in latency, cost, speed, etc. And we will show you some of these in the demo shortly. Oh, Cedric will show you some of these in the demo. So why is this a huge opportunity? So this is how we actually are building Red Hat Enterprise Linux. So Red Hat Enterprise Linux AI, we essentially use bootable containers to stack the different components on top of that base image, as we have different components for, say, model fine-tuning, training, components for model serving, and various other utilities that comes with the appliance. So this allows us to version these dependencies in a way to make things much less complex. For example, the training component PyTorch, the inferencing component VLLM, and then the AI model on top, and everything having all this in one standardized way to put everything together. And lastly, assembling these parts in build time brings so much more stability than trying to patch them in production. And now for the fun part.
Woo!
Ooh, let's see some
Who
demos.
wants to see a demo?
Woo.
Awesome. Okay, so let's do it. Again, we talked about the extension, right? So you can go to the catalog here in Podman Desktop and you can install it. It is another container, so it's container within a container, very meta. But essentially, you're able to build from an existing bootc container. We're going to show you how to get that bootc container. It takes about 2 to 5 minutes, depending on your internet connection, the hardware that you're using, but you can build for that specific architecture. And just released about a month or two ago, there's an extension, a capability that allows you to run the VM inside of Podman Desktop, which is also very meta, but it's very cool as well. So let's go ahead and check it out. So what we're doing today, again, as you saw in the abstract, is this code generation. So we're going to test out the application locally within containers. And then we're going to go to this next stage, which is, hey, how can I convert this to a disk image and use it remotely and do these updates? So this is the whole pipeline that you're going to see today. And we're going to use, actually, what's known as the AI lab recipes. So it's a collection of different popular use cases that developers and operations teams are already using today, so that you don't have to rebuild the wheel, right? So in Podman Desktop, and that's AI Lab. So I'll show you. So we got bootc, and you can install this from the catalog here. And so actually, I'm going to use a combination of AI Lab and the Bootable Containers extension. So you can see here that this is kind of the dashboard where you have some help articles, how to get started. And if you have any existing bootable container images, they'll be here, and you can go ahead and start to build them just like that. And you can see, hey, what builds have failed, progressed, see their location here, and examples. So maybe you want to boot Tailscale, or say a Wi-Fi bootable container, or a QEMU for virtualization. You can do that here as well. So what I'm going to go and show you is the example of running one of these applications locally on my machine. So there's a lot of different use cases, graph rag, function calling for agentic, but we're going to start off with this code generation. So here we have the local clone of this repository here, and I can show you this real quick if you're interested. But this is where the source code is located for these different recipes. And the recipes have all the components of, hey, if I need a model server, if I need that front-end application, and the model itself. And I'm going to go over here, and I'm going to go ahead and open this up in VS Code. So here what I have, let me make this a little bit bigger, is essentially a repository that includes not only the application we want to run locally, but also a bootable C container file that we can build this specific workload with. So let's go ahead and start this locally. So I'm going to show you we're going to be using this Granite 3.3 model. If I have another model I want to use on Hugging Face, I could just pull this in. And here we're working with quantized models just because full safe tensors would be too resource intensive. But what happened is we built the pod that's running this application. So if I actually go back over here, we can see 8 seconds ago, we've got this podified application. And here we have the ability to kind of inspect, get the Kubernetes manifest, et cetera. I'll come back here. And let's go ahead and start this. Anyone have a request of what they want to see the model create? It's code generation, so it could be anything. Or just give me a language. Lisp?
Common Lisp, okay.
An example. Is that how you say it?
Yeah, 2 words. Common
yeah. I've never worked with Common Lisp. But let's see what it says. All right.
Does the brackets match?
Yeah. Will this compile? Likely? OK, sweet. So cool. So we've got this application running locally on our system using our kernel. But if I come back here, what I'm going to do is use this bootable C container image in order to go ahead and build this out so that we can deploy it on a system. So we're going to copy in our SSH key. So this is going to use your local SSH key. It's going to find it and add it here. We got a couple arguments here. For example, we're using this specific model. So let me come over here and let's check it out. So it's Mistral specifically for code generation. You could use, say, for example, an Ollama model because Ollama is also using OCI. You could use Hugging Face, put it in a container, or maybe Ramalama as your inference server. So I'll come back over here. You can see that by default, we're using a pre-built image. But let's say, for example, I want to use this and maybe add only write in Common Lisp. And then our developers are going to be very confused. We can start making changes to the app there and add that to our container file so that we build it there as well. And a server image. So here we're using Llama C++ Python upstream. You could use Ramalama, Ollama, whatever your inference server is. Maybe it's VLLM or something like that. And we're also going to add the quadlet files to essentially turn this into a systemd service, right? So we've got this, if I go over here, a couple files here for a .kube and a .image. So .image, in order to kind of help with this quadlet creation and run it as a systemd unit. But then also a .yaml here, so I could take this to Kubernetes, or I could also use it with Podman. So we're pointing here to the inference server. We're also pointing to which ports we want it to be on, et cetera, et cetera. So let's come back over to the original container file, and we can see that hey. We're also adding these podman commands, which is the most important part because this is kind of pre-polling the images so that we don't have to wait when we actually run this system disk image. And let's go ahead and test this out. So I'm going to come down here in the makefile, and the makefile is going to tell you, the makefile is going to help us build this, but the README, is what I was trying to get to. Kind of has some instructions on what you can do with this repository, and it's essentially a makefile to build this. We could do it just using Podman as well, but this makes our life a little bit easier. And I'm also going to tag this, so we're going to say bootc image, and we're going to call it key or que, whatever you want to say it as, and we'll call it code gen bootc. And then I need to pass bootc as well. Did I? Don't worry, I ran the command earlier, so we'll be OK. Oh, OK. Yeah, I just noticed that. Hold on, I'll just jump in here. I made a last minute change, and I knew I shouldn't have, but that's what happens when we're at conferences. Okay, so.
Speaking of common Lisp, I used to dream in Scheme. Scheme is a dialect of Lisp, so that's pretty. Well, that was a long time ago as well. I was doing not AI, more like expert systems and machine learning in college, more than 20 years ago. So.
And then we'll call it cogen boot C. Oh, and then we'll give it pat boot C. Okay, so we're kicking off that container file. Here you can see we start off with that from, so we're using that specific image, adding in our SSH key, and we're building it to be here specifically. And of course, next step I would do is, hey, podman push that specific image to our registry, right? So we'll go ahead and do that. I don't know if it'll work on this internet, but I've actually already got it pushed just in case. So it's already here on key.io, Quay. And I'll go ahead and show you, hey, I've got my demo app, for example, but hey, I also have the bootc image. And it's about, I think, 8-9 gigabytes in total. We're including the kernel, all those packages. Actually, about 6 gigabytes. It's not too big. And let's go over to the extension here. So I've got this here within my local registry. Let's go ahead and build this. So I'm going to specify the output folder here. Let's just call it DevConf. And the file system, we could select that, or say, for example, provide additional configurations, specify the kernel arguments, users, or maybe public keys that we also want to add as we build this image. And kicking it off is actually going to just run this podman command here, where I'll kind of explain what's happening, but we're essentially calling it, giving it that name, privileged container. We're also giving it output where we want the resulting. Oh, okay. Oh, shit, 2 minutes left. All right. And what we're doing is we're using this image here called the bootc image builder. So if I go over here, I'll show you. You can see it on Quay, but I also have it open here, bootc builder. And so this is the bootc builder where if you want to pass specific arguments and commands, you can learn how to do that here and build for those different file systems and also different, QCOW or Amazon, et cetera, et cetera. So you can learn more about that here in this repository. But let's come down here. And I've actually already got a pre-built version for you. So it delivered me this ISO here earlier today. So we've got this boot ISO, install ISO, and then I'm going to go to UTM. UTM is a way to run QEMU on Mac, but like way easier. It's very nice. And I'm going to go ahead and I've already kind of installed this. I'm going to show you it already running on my system. And let's go ahead and just make sure that the application is running here. So again, we've taken from Podman Desktop and that command, this artifact here, this ISO. We could deploy this wherever we want. I'm deploying it locally. And here we have on our local host, 192.168.64.7, the application running on that port. Ooh, well, let's see what I'm doing here. 192.64.7. There we go. All right. So now it's running. And so we could do that command again to get the common Lisp code. I'm also going to hop into the terminal. And let's go ahead and do a SSH so I can show you bootc before we run out of time. So we'll do root 192.168.64.7. Again, SSH key is already passed. And then let's do a, 1 second. Let's go ahead and do the, We're
basically running into our Q&A time.
Oh, sorry, code gen. Oh, I can't spell. Gen. Awesome. So we can see because of the quadlet system, quadlet unit that's been created, we've got our application that we saw earlier running as a systemd service. But if we also do podman ps, we can see those containers have all been pulled locally. So we've got the inference server, we've got the cogen, so the actual front end of our application. And if we go to bootc, well, this is where we have the ability to do these upgrades and these maintenance activities. So if I do bootc status, we can see, hey, we're using this specific booted image, right, that I had pushed to the registry earlier. Or maybe we want to do an upgrade. So maybe I could set a cron job to do this automatically, or we could go ahead and do this manually. So I'll go ahead and first check. So make sure that, hey, something is up there. It looks like earlier today, I went and did an update. So I made some updates to that original application. And so we've got new layers that we can go ahead and copy in. And if I were to go ahead and do this, hey, bootc upgrade, what's happening here is it's going to fetch those new layers. It's going to queue them up. And the next time the system reboots, we've got that new operating system as an immutable unit. So we don't have the full time to do that, but that's just a quick demo of using bootc and upgrading these systems. But I know it's the Q&A time, and I hate that this went over. So let me come back to our presentation. So thank you guys for staying with us. Let's do some Q&A if you're interested, and thank you for your time.
Any questions?
I know it was a quick demo, so I apologize.
All right, so this might not be exactly the topic, but what are the ways of distributing the images of bare metal? Is there some fixed integrations or some other stuff, or is this has to be homegrown?
On what, sorry? Oh.
EXE, for example. I want to boot my image from my bare metal fleet. What tooling does the project provide?
So, yeah. So we're talking about distributing this bootc image on, say, bare metal. What was that demo that was? Were you at the keynote this morning? So there was a cool demo. What was the project called? It was cockpit. What was the? Yeah, was it cockpit?
All right, so there is something.
Yeah. So just like how on say for example RHEL or Fedora, there's is it cockpit that manages? Yeah, Firefly. There's a new tool that's being developed essentially, and I'll talk to you after, but it essentially allows you to do all of this management of your bootc images to your fleet. Flight control, yeah. So it's a new project. I actually didn't know about it until just recently. But yeah, flight control, CTL, is the project that allows you to do this kind of fleet management. And so I hope that helps. I haven't tried it out yet, but it's quite a new project and looks very promising. Any other questions? Yeah, we'll give it a second. Hey.
Can I answer this question?
Yes, please.
You can still pixie boot Anaconda and so in the Kickstart that before we see it. Now Anaconda
Thank you. I owe you a beer. Well, cool. If you want more demos, come see us in the AI Upstream booth, which is outside of the keynote stage.
We'll be there for only 1 hour because we have the workshop.
Oh, yeah. One of us will be there. But thank you guys for coming. I hope you try out the extension. I hope you try out these AI Lab recipes and enjoy the rest of the DevConf. Cheers.